everyone. Thanks for joining this session. My name is Denis Kovalenko. I work at Bolt. And I was actually the first person to work on ML infrastructure and ML ops topics at Bolt. Joined more than 4 years ago. And currently I'm engineering manager for our ML platform and experimentation platform teams. And today I'll be sharing our learnings on how to empower data scientists and ML engineers to be efficient with software and tools. And for that, I'll talk about a few things. First of all, I'll raise a question. Does it actually make sense to work on centralized platform or tools in the age when there are so many software systems already out there that can solve many parts of the problem? I will share about ML platform at Bolt, and more specifically the principles we've used to develop it and work on it. And then, since everybody's talking about data drift and data monitoring, I'll share how we approach this problem at Bolt and use it as an example of our approach enabling teams to be efficient. And I think efficiency is key. Today, everybody talks about efficiency, especially in the lights of the dark news and things happening with layoffs in tech. But for us at Bolt, efficiency is nothing new. Since we started out 9 years ago as a small company in Estonia, and now we are in more than 40 countries with 100 million customers, with a lot of machine learning and data science being part of the product, since we compete against some of the biggest names in the world and been competing always, we had to find a way to be efficient, achieve more with less, and machine learning plays a big role in that. But for me, efficiency in product development comes to two things. First is choosing what not to build, so that you can save the time and focus on things that actually matter. And when you do build something, thinking on how can you achieve more with less. And I think we've been very successful since we've reached our current level with way less resources than all our peers in the industry. That's great. How does this relate to machine learning? Please raise a hand if you've seen this diagram before. Please lower your hand if you have seen it yesterday for the first time at this conference. All right. So some people have seen it before. That's wonderful. This comes originally from the great paper, Hidden Technical Depth in Machine Learning Systems. And in my opinion, this is the paper that kicked off the whole MLOps field. And essentially, it has two takeaways for me. First is that interest rate on the technical depth in ML systems is much more expensive than on usual software systems. So you have to be way more careful with this, it's like credit card versus mortgage interest rates. And the second one is that in mature systems that bring value to customers, ML core is only a small piece of the equation. And there are many more problems that have to be solved around data, infrastructure, and tooling. When this paper was initially started out and published, there was not too many specific tools for ML. And you had to, combine whatever you could find online, unless you worked at a company like Google or Facebook. Today, the situation is much different. There are so many tools from open source, cloud solutions, and startups providing a solution to almost any problem. And just picking what to use can be quite overwhelming. You could, of course, thinking about efficiency. One way to look at that is we have so many great tools out there. Let's enable the product teams, the teams that actually build ML features, to choose whatever tool for the job they want. And they'll be efficient because they can use the tools they like, use that seem to be the greatest, and fit their use case perfectly. That's one of the way of doing that. And if you have one or two models, that could be the perfect way. But to think how to scale it out for the organization, hoping that you will have more and more ML use cases in the company, we have to understand a few concepts. I borrowed a slide from Ville, who was the ML infrastructure engineer at Netflix, and he's the person behind Metaflow. And essentially, it covers the idea that the lower you go down the infrastructure stack, the less data scientists care about the things happening there. At the same time, it requires more infrastructure and more software and more complex problems to be solved. So combine that data science may not necessarily care about those pieces, and combine it with the that is further away from value. Let's think whether allowing everybody to choose whatever they want will scale well if you have more than 50 plus projects, as we do. It will start nicely. The first team, the pioneers of ML, will solve their problem. They get their model out. They choose whatever they want or whatever they can at that moment in time, and they'll get to production. But the second team might have slightly different use cases. They might have slightly different needs, different problem. So they might choose to use something else, use, I don't know, weights and biases instead of MetaFlow, MLflow. And you'll have a bit of duplication. So there will be, things will look mostly the same, but you'll pick maybe a bit of different tools along the way. But then you have a third team, and fourth team, and fifth, and sixth. And this doesn't look pretty on the slide. It looks messy on the slide. It looks much messier in real world. Since each of those boxes has to be understood by somebody, it has to be maintained, supported, and worked around it. Let's agree, there are no perfect tools, and every tool requires working around it and dealing with it and solving the problems that arise as you grow and scale and go to more advanced use cases. At Bolt, we believe that teams shouldn't solve the same problem over and over again. It's the opposite of economy of scale. It's the opposite of efficiency. And sometimes for efficiency, you have to make choices that may look weird. For example, at Bolt, backend engineers can only use TypeScript and Node.js in production, and all data scientists are using centralized platform. And the choices are limited. And what it actually means is that my team is focusing on solving this lower part of the stack and providing abstractions, as well as solutions behind those abstractions that work in 90% of cases out of the box and work really well. And to go forward and actually get to details and how we do things and get a bit more to details, I think we should understand this part first. This is the quote by my colleague, very smart engineer, and this is one of the guiding principles we've been using at Bolt. Instead of focusing on implementation, I get asked quite a lot, so what's your ML platform? What do you use? What do you use for this? What do you use for that? My answer is usually, it doesn't really matter. Your problem might be different from ours. You might have different data. You might have different needs. You're at different maturity level. And if you're starting today, you have different choice than we had when we implemented or solved this problem 3 years ago or 4 years ago. That's why the key is to understand which problems you are solving as an organization, where are the overlapping components, and build good abstractions and some kind of implementation. And as long as you can do that, you can improve implementation, you can pick different technologies, you can do migrations without bothering client teams too much. And this is where this whole infrastructure-agnostic teams come from. Infrastructure can get better, and we hope the software and tools will get better over time. But we want to make sure that teams don't have to rewrite and re-architect their whole solution from scratch every time there is a new tool out there. Now, let's get closer to the details of this. How do we actually approach looking at data science and ML within the company? Everything starts with a template in a monorepo. So we have a monorepo. All data science ML projects are in this repository. All of them follow the same template. And this template provides a structure and provides abstractions over common things that exist in ML projects. This includes querying the data from data warehouse and getting the training data, pre-processing it, training your model, using this model in inference step, testing your model, monitoring the data of the model. So we provide the wrapper and a structure where essentially you need to fill in the gaps. And having that, you have something that fully runs locally. It's a vanilla Python that's Dockerized, and we have a bunch of scripts that help you to kind of look at this as a holistic part of the pipeline. But when you want to get to production, you don't have to choose, you don't have to implement the production pipeline as data scientist or ML engineer. Because we have something called AirPipe, which is our internal framework that's taking this code that you have in your data science repository. And from the configuration, we generate full workflow that implements all the best practices of MLOps and does it essentially for free for you. And since we own this abstraction, since we own those components, and everybody is doing things in a centralized and this kind of coherent way, we are able to plug in components, solve bugs, and add new features easily for all our users. Now we have more than 30 data scientists in the company, and we have 50 plus projects, and this allowed us to scale and solve problems once and for all. Now, let me show you how it looks. I know it's quite small, so don't expect you to read it. And also, I'm here in the box, so I'm forced to not go out of this box. That's why I cannot show you here on the screen. So try to bear in mind with me. So this is like one of these pipelines that is generated from this configuration about your project. And it does things from building the images and running tests, capturing the metadata of the run, extracting data from data warehouse, and then it does this forking. And let me explain what it does. At Bolt, we want to create the best possible experience for every given city. Cities are very different. Data from one city might not transfer well to another on one side. And on the other side, we want to empower data scientists to use whatever tool they want or know. And since we have a lot of data, if you try to solve the problem for all cities at the same time, you would have to go to distributed frameworks very soon. So the way we solved it, and this is the approach we've been taking for 3+ years, is that we split the data on the framework level by city. And as data scientists, you write a code that needs to get the model out for a single city. And then we combine it all in a kind of whole holistic product. Then we have a bunch of things around testing, deploying it to staging, running a variety of checks. And if things are good, you can gradually roll it out to production. And this is something that is available for you out of the box. And there are many, many things interesting happening here under the hood. But this is a small pipeline. This is just a toy example so that you can actually read something. And in reality, most of our mature models look more like that. That's a modern piece of art, if I may say. So we have hundreds of parallel branches, and retraining some models takes, consumes thousands of CPU cores in parallel. But from perspective of data scientists, it's just I just write a script, using whatever I want. And this allows us to get very far, very fast. And when you have hundreds of things running in parallel, there are inevitably complexities. Different cities might require different size of machines, and you don't maybe necessarily want to manually specify which instance type to use for every single city. So we have components under the hood behind our abstraction of training for selecting the appropriate instance based on the historical metrics from the previous runs and many, many other things to work around the cloud issues, moving things from default region to another region if there is not enough capacity and things like that. But that's something that we kind of hide behind abstraction training. Now I just want to kind of give you the keywords to ask me about later in networking part. So some of the things we have on the platform. So feature store, we've built feature store before it was mainstream. So we started out in 2018. And I think one of the differences is that for us, feature store actually is way more used not in machine learning than in machine learning. It's used a lot by usual backend engineers and data analysts to take the analytical data from data warehouse or streams and use it to empower real product with a variety of say interesting data points that are hard to compute in the backend. And we've saved so many months of engineering time with those things. And of course, it's using machine learning. And here comes the second abstraction that I want to talk about. And it's very simple abstraction. And if you're in microservice architecture, I totally suggest you to check it out. So we have something called model invoker, which essentially is a very simple microservice that is a gateway to all machine learning models running in real time. So instead of client teams and backend teams integrating directly with ML models, whether they're on SageMaker or on Kubernetes or wherever they might be, they integrate with the usual Node.js service like any other, and they don't care where it runs under the hood. Initially, we started out with running our machine learning as transpiled to JavaScript, embedded as a JavaScript library into the actual servers of client teams, like pricing teams or geo teams. But then by moving this behind abstraction, we've been able to migrate from JavaScript to Python, whereas our Python infrastructure became more mature. We have done a lot of things and re-engineering on how we serve our Python models, and we will do more migrations going down the line. At the same time, client teams don't have to be worried about that, and data scientists will not be exposed to much and will not have to rework their stuff because they wrote the code. Where it runs, that's kind of implementation detail. As software engineers, we know that abstraction implementation details shouldn't matter to clients most of the time. And this got us pretty far. Since we started the team working on ML infrastructure 3 years ago, now we got to quite mature state where we have more than 800 pipeline runs every single month, like the one I've showed before. So getting the data, training the models, testing them, and getting them in some way to be used in the real world. And now we have billions of live ML predictions happening every single week in real time. And this approach we've taken allowed us to do that without data scientists relying on engineers. As data scientist, you get started, you use this you write your Python code, infrastructure and systems take care of getting this behind the kind of this production line. So you don't really need to rely on engineers. And a single data scientist can own the project from prototype to impact and iterating on it in the real world. This is the power of abstractions and solving these things for everyone. And try to guess. First of all, have you guys used Bolt? It's like the Bolt ride scooters. Okay, not every one of you. So we have some work to do still here in Stockholm. Try to guess, for every finished order on the platform, how many machine learning predictions are being made? Give me a number. Who is brave? Right, you'll have to be brave. You have a notebook, right? Okay, 5 predictions. I have 5. I do have more. 1, 2. What? 100. Who said 100? Oh, good. You're very close, sir. If this was an auction, you would win, because we do more than 100 ML predictions for every single order. You might be wondering where we do that, and I mean there are many cases, but efficiency is the key. So for us, optimizing how do we assign driver to an order, courier to a rider, how do we use it to properly compute, have more accurate ETA? How do we prevent bad guys from happening? How do we choose the optimal price to kind of optimize the whole output of the marketplace and available supply of resources in the system? There is a lot of decision making happening. So we're in quite mature stage right now. That's why I think but we started quite small. That's why I think our learnings can be transpiled to almost any team. But this also means that now we have to kind of switch our focus from how do we get the first version live, how do we get to production, how do we get to the impact, because we've been through that already, to how do we empower our data scientists and ML engineers to iterate on their models, whether it's just refreshing the data and retraining the model, improving the model performance, or implementing new features and new support. And you cannot do that safely and be confident if you don't have good support on the tooling side. Otherwise, every release will be a scary thing and you will postpone it, and you would almost never train models. Learning we saw is that once we got to the mature state of our systems, people start to retrain and refresh their models much more frequently. No brainer. If things are easy to do, people do them more frequently. So for that, I want to talk about case study of building ML data monitoring component. Since data drift and model monitoring is like teenage sex, everybody talks about it. I have not met that many people who have done it. So if you have great data drift detection, let's talk afterwards. Because I've also been talking about it for more than 4 years, but it was too hard of a problem and seemed not important enough for us to solve, at least in our use case, on our problems. That's why it took quite a while to us to get to production. Not too ashamed to admit with it. We've been working on more important problems. And let's do a quick recap. What's up with data? Why it's important to monitor the data. First of all, we have to admit data drifts and data skews are a reality. Whether it's a lockdown or a seasonality change or a new competitor activity, data may shift and change in the real world due to a variety of reasons. And of course, it can change because of the upstream issues. Some bug in upstream system, or somebody forgot or didn't know that some column in their system is being used to pass to a model, can affect you. We had example when instead of minutes for the predicted time of arrival, software upstream start to send it in seconds. And one of the very important features suddenly has become, the mean value was multiplied by 60. You can imagine what happened to all the models that were predicting the prices and time of arrival and things like that. So, and detecting those things sometimes can be really fast if things get broken. But if this is like maybe a marginal feature that has been like maybe not the most important feature, you might not detect it unless you have really strong validation on your inference layer. This means you might have something that's not working for years and degrading your performance a bit, and you don't know about it. And the reason why nobody has like really looked too much into that is that it's quite hard problem. It's quite challenging on infrastructure side to connect all the systems and make data comparable, so you can actually run your fancy comparisons and measure distance between the distributions and things like that. But we saw that it's a common problem. It's maybe too expensive to solve for a single project, but now that we have many projects with tabular data, it made sense for us to invest into that. So let's build a common solution. We've been quite inspired by the paper, TensorFlow Data Validation, Continuous Monitoring of Data in ML Pipelines. It's quite an old paper, quite good read. I would totally recommend it to you. And there is a follow-up paper on that. And we have implemented their reference architecture. It all starts with the data. We have the data. Then now that we don't only train the model, we also collect statistics and extract the schema. And based on that, we can automatically build constraints that we can compare the production data against. So now that when the model is deployed, we are able to as well collect the data from different systems and also extract the same statistics. So we have understanding how data looks like in for model training, how the data looks for the model in life, and now we can kind of validate them. And if detect if something is wrong, we can notify the model owner for them to either fix alert if it's a false positive and adjust the schema, or fix the actual underlying issue. And here you may notice I'm not showing any technology. We're at infrastructure-agnostic ML platform talk. And as data science, you don't really need to know how those things work. And one of the things that kind of is clear is that in this problem, plumbing code and connecting all the data and making, connecting all the dots so you can actually compare data frame and training and data frame and inference is the hard part. And this is the kind of something that can be leveraged and scaled and reused across multiple cases. So we have implemented it. And since we own the abstraction of training pipeline, we've been able to inject it. There's this prepare monitoring input and output and build constraint step that can be easily injected into any training pipeline by just providing configuration saying this model should be monitored, more or less. And now that we have this part implemented, we can, for every model that's monitored, we can able to launch the pipelines that will look for all the versions that are running in production and essentially fetch the data from those production versions and compare apples to apples. The data that this model version receives to the data that this particular model was trained on. So we can always compare apple to apples. Because maybe you trained the model in August. So comparing this week's data with last week's data doesn't make sense. So you need to make sure you compare apples to apples. And by having that, we are able to do things like comparing how the data looks like in training and production, things like that. Here we use TensorFlow data validation, kind of profiling. And we can also alert the owners. People who pay a lot of attention and who know the tooling in the space will notice that this is TensorFlow data validation, and this is great expectation. This is one more example of infrastructure-agnostic tooling. Initially, we built this architecture around TensorFlow data validation, but since we saw so many problems there and it's not well maintained, we found that great expectation actually is doing way better job. So we replaced it very easily and this I think is one of the things that you can take away. If you do things in a proper way and have a good abstraction, like data monitoring or training or deployment, you can swap out implementation very easily. So right now we replaced with great expectations and it's been liked by users way more. And as a result, we got to the stage that this data monitoring takes not too much time to an effort to onboard in happy cases. So very easy to adopt. Instead of having to do a lot of software engineering, data scientists just need to provide and customize a bit the schema and write a few lines of Python. It's kind of plug and play, can be embedded into every pipeline that we currently use on our system. And so far, in every project where we adopted to, it detected at least one data issue, whether it's the upstream issue or the kind of training serving skew and the logic of a feature computation is different. And we started quite small. When I joined the company in 2018, we had few data scientists and few ML projects in production. And now we've grown quite a lot, both in terms of data scientists that my team supports, as well as the number of projects. But the principles behind on how we build the tooling and which tools we build didn't really change. And we use a mix of cloud solutions, open source solution, and in-house solutions, but the abstractions are remaining the same, and abstractions outlive the technology. I know that everybody here is in a different stage. You might have you have different maturity stages in the company, you have different size of the teams, there are different problems you're solving. But I believe that the main key points can be applied to everyone. Focus on understanding the common problem you have an organization across a variety of ML projects. Define an abstraction and have some kind of implementation behind it. And then you can plug in things to this abstraction and you can improve it. And this can allow you to add new features. For example, optimizing the costs, selecting right instances, moving some workloads to in-house, let's say, infrastructure instead of cloud managed. As well as add things like data monitoring components and automated testing. We've done quite a lot of interesting things with testing. Feel free to ask afterwards. And migrations are always pain. We are going through very painful migration right now on data warehousing side. But by having this abstraction on how to interact with data warehouse or how to interact with any system, migrations can be faster and a bit less painful, or at least more contained and can be done faster. And I think the most important part is if you do things in a centralized way and provide good solutions, teams can actually focus on adding value and solving the actual problems of customers, not on debating which tool to adopt, because we saw from the chart that they don't really care about those tools. You just want your stuff to work. And in this way, you can enable teams to be more efficient, get more stuff done faster, and let teams switch between projects more easily as well, because things are consistent and unified, and it's much easier to adopt best practices. I want to thank you, and let's have a chat afterwards.